Welcome to this coding problem walkthrough. In this session, we'll tackle LeetCode problem number 1807, titled Evaluate the bracket pairs of a string. Together, we'll explore the problem, break it down step by step, and review different approaches to solve it. Let's dive in. In this problem, you are given a string S that includes some substrings enclosed in round brackets, like key. Additionally, you have a knowledge list that contains pairs of strings. Each pair in this list represents a key and its corresponding value. Essentially, the knowledge list acts as a dictionary where you can look up the value associated with a specific key. Your task is to replace each bracketed substring in S with its corresponding value from the knowledge list. If a key inside the brackets does not exist in the knowledge dictionary, you will replace it with a question mark. Finally, you return the updated string after making all the replacements. The input string S can be quite large, up to 100,000 characters, and the knowledge list can also contain a large number of pairs, so efficiency will be important when solving this problem. The output of the problem is a single string that represents the evaluated version of the input string S. To help clarify, let's look at an example. Suppose the input string is name, is age, years old, and the knowledge list contains the pairs name, Alice, and age, 25. In this case, the first bracket pair, name, corresponds to the key name in the knowledge dictionary, which maps to the value Alice. So, name is replaced with Alice. This process is repeated for all bracket pairs in the string. Now let's continue with the previous example. The second bracket pair, age, maps to the key age in the knowledge dictionary, which has the value 25. So, age is replaced with 25. After replacing both bracket pairs, the final string becomes Alice is 25 years old. Moving to another example, if the input string is hi, name, and the knowledge list only contains the pair a, b, the key name does not exist in the knowledge dictionary. Therefore, name is replaced with a question mark, resulting in the final string hi. Let's look at one more example to solidify the concept. Imagine the input string is a, and the knowledge list contains a single pair, A, B. Here, the bracket pair, A, corresponds to the key A in the knowledge list, which maps to the value B. Each occurrence of A in the string is replaced with B. After processing all the bracket pairs, the final string becomes B. This example demonstrates how repeated keys in the string are handled consistently, and each bracketed substring is evaluated independently. Finally, let's discuss the constraints and some edge cases you may encounter. The string S can be very large, up to 100,000 characters, and so can the knowledge list, which can have up to 100,000 key value pairs. Each key and value in knowledge will always be a string of lowercase English letters, with lengths between 1 and 10. The string S itself consists of lowercase English letters and valid bracket pairs. For edge cases, if the knowledge list is empty, you must replace all bracket pairs in S with a question mark. If S contains no bracket pairs, simply return it unchanged. Additionally, if S includes consecutive or nested brackets, treat each bracket pair independently and replace them one at a time. Lastly, any key in S that does not exist in knowledge should be replaced with a question mark. These constraints and edge cases provide important guidelines for implementing an efficient and correct solution. To start, let's explore the brute force approach, which relies on a straightforward string replacement strategy. The idea is to traverse the string character by character, and whenever we encounter an opening bracket, we extract the substring enclosed within the brackets. Then, we perform a lookup in the knowledge list to find the corresponding value. If a match is found, we replace the substring with that value, otherwise, we replace it with a question mark. While this approach is simple to understand and implement, it has significant inefficiencies. For each bracketed substring, we repeatedly search through the knowledge list, which takes linear time relative to the size of the list. As a result, the time complexity becomes O, and *m, where n is the length of the string, and m is the size of the knowledge list. This makes the approach impractical for larger inputs, as the repeated lookups create a lot of overhead. Now, we turn to an optimized approach that uses a hash map for quick lookups. The intuition here is to convert the knowledge list into a dictionary, which allows us to perform lookups in constant time. With this in place, we traverse the string once and dynamically build the result. As we encounter bracketed substrings, we can immediately retrieve their corresponding values from the dictionary and append them to the result. This eliminates the inefficiency of repeatedly searching through the knowledge list. The process involves three main steps. First, converting the knowledge list into a dictionary, which takes time. Second, traversing the string in a single pass, which takes time. And third, building the result dynamically using a temporary buffer to minimize additional string manipulations. This optimized approach significantly reduces the overall complexity to n plus m, and is well suited for handling larger inputs efficiently. The optimized hash map solution is the chosen strategy due to its balance of efficiency and scalability. The brute force approach, with its (m) complexity, is not practical for large datasets, whereas the hash map approach ensures lookups and a single pass traversal of the string. This streamlined process avoids redundant operations and builds the result dynamically, making it both faster and more efficient. The key insight here is that a dictionary is an ideal data structure for mapping keys to values, enabling quick substitutions without repeated searches. While this approach does require additional space to store the dictionary, the trade-off is minimal compared to the performance improvement. Moreover, although the implementation is slightly more complex than the brute force method, it handles large inputs gracefully. Overall, this strategy delivers an optimal combination of speed, clarity, and scalability, making it the best choice for solving this problem. The problem we're tackling involves a string, s, which contains placeholders in the form of key. Alongside this string, we are given a knowledge list, which consists of key-value pairs. The task is to replace each key in the string with its corresponding value from the knowledge list. If a key is not found in the knowledge list, it should be replaced with an empty string. For example, given a string like hello name and a knowledge list containing name Alice, the output should be hello Alice. To solve this, we'll start by parsing the input. We convert the knowledge list into a dictionary because dictionaries allow for average time lookups, making replacements efficient. Next, we initialize two variables, a result list to build the output string incrementally, and a pointer I to traverse through the string one character at a time. To process the string, we iterate character by character using the pointer I. If the current character is not an opening parenthesis, we simply append it to the result list and move the pointer to the next character. However, if we encounter an opening parenthesis, this signals the start of a placeholder. At this point, we use another pointer to locate the closing parenthesis, that marks the end of the placeholder. Once we've identified the complete placeholder, we extract the substring inside the parentheses as the key. This key is then looked up in the knowledge dictionary. If it exists, we append the corresponding value to the result list. If it doesn't, we append an empty string instead. Finally, we advance the pointer I to the position right after the closing parenthesis, ensuring we continue processing the remainder of the string. Once all characters are processed, we combine the elements in the result list to form the final output string. There are a few critical insights that make this algorithm efficient and robust. First, using a dictionary to store the knowledge list allows us to perform key lookups in constant time, which is crucial for handling large inputs efficiently. Second, building the output string incrementally using a list and only joining it at the end is a space-optimized approach. This avoids creating multiple intermediate strings, which would otherwise increase memory usage. Third, the use of two pointers ensures that we traverse the string in a single pass, resulting in an overall time complexity of n. Additionally, the algorithm handles key edge cases gracefully. For instance, if the string contains no parentheses, it is returned unchanged. If the knowledge list is empty, all placeholders are replaced with empty strings. It's important to note that the input does not account for nested or malformed parentheses, simplifying our implementation. The combination of these techniques ensures the algorithm is both efficient and practical. Now let's analyze the complexity of the algorithm. The time complexity is n, where n is the length of the string s. This is because we process each character exactly once, and dictionary lookups are 1 on average. The space complexity is k plus n, where k is the size of the knowledge dictionary and n is the length of the result list. To better understand how the algorithm works, consider this example. Suppose the input string is hi, name, welcome to, place. and the knowledge list contains name, Alice, place, Wonderland. The goal is to replace the placeholders, name, and place, with their corresponding values, resulting in the final output string. Here's how the algorithm executes step by step. First, we convert the knowledge list into a dictionary for quick lookups, name, Alice, place, Wonderland. Then, we traverse the string S. We start by appending the substring hi since it contains no placeholders. Upon encountering name, we replace it with Alice and add it to the result. Next, we append the substring welcome to, which also contains no placeholders. We then replace place with Wonderland and append it. Finally, we append the exclamation mark. Combining all these parts, we get the final string, Hi Alice, welcome to Wonderland. For an edge case, consider S equals hello, key, and an empty knowledge list. Since key has no match, it is replaced with an empty string, resulting in the output hello. This demonstrates how the algorithm handles missing keys effectively. This Python implementation solves LeetCode problem 1807, evaluate the bracket pairs of a string. Let's break it down step by step. First, we are tasked with replacing placeholders of the form key in the string S using a mapping provided in the knowledge list. If a key is not found in the knowledge list, we replace it with a question mark. 1. Convert knowledge list to dictionary. The knowledge list is converted into a dictionary, knowledge_dict, for efficient lookups. This is done using a dictionary comprehension, where keys and values are extracted from the knowledge list. 2. Initialize result list and pointer. We initialize an empty list result to build the final output string, and a pointer I to traverse the input string S. 3. Traverse the string. The while loop iterates over the string. If a character is not the start of a placeholder, we directly append it to the result list. For example, plain text outside placeholders is handled in this manner. For handle placeholders, when a is encountered, it indicates the start of a placeholder. We use a secondary pointer j to find the closing and extract the key inside. The key is then looked up in the dictionary using knowledge_dict.get key ? Where the default value is if the key is missing. 5. Append replacement or the value corresponding to the key, or if the key is missing, is appended to the result list. The pointer I is updated to skip past the closing parenthesis. 6. Build and return final string. After processing the entire string, the result list, which contains all characters and replacements, is joined into a single string using .join, result, and the final result is returned. This implementation efficiently processes the string in O, n, time, where n is the length of the input string S. It handles edge cases such as missing keys, empty knowledge lists, and strings with no placeholders gracefully. The use of a dictionary ensures fast lookups, while the result list provides an efficient way to construct the final string without repeated string concatenation. Here, we start by defining the solution class and the evaluate method, which takes two inputs, a string S and a list of knowledge pairs. The first step is to convert the knowledge list into a map for efficient lookups. Using a hash map, we iterate through each pair in the knowledge list and populate the map with the key value pairs. Next, we initialize a string builder called result to construct the output string efficiently, and we set up an index variable I to traverse the input string S. As we loop through the string, we check if the current character is an opening parenthesis. When we encounter one, we know a key starts here, so we initialize another pointer j to find the corresponding closing parenthesis, by iterating forward. Once we locate the closing parenthesis, we extract the key from the substring between I+1 and j. Using the knowledge map, we append the value corresponding to the key to the result. If the key is not found in the map, we append a question mark instead. Finally, we update I to skip past the closing parenthesis and continue processing the rest of the string. The remaining part of the code handles cases where the current character is not part of a key. If the character is a regular one, we simply append it to the result and increment the I pointer to move to the next character. This process continues until we have traversed the entire string S. Once the loop finishes, we use the toString method on the string builder to return the final evaluated string. This implementation ensures that each key in the input string is replaced with its corresponding value from the knowledge map or a question mark if no match is found, while preserving all other characters in their original order. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. To analyze the time complexity of our solution, we start with the process of building the knowledge_dict dictionary. This involves converting the knowledge list, which contains k key value pairs, into a dictionary. Since this operation requires iterating through the list once, it takes k time. Next, we move to the traversal of the string s, which has a length of n. The algorithm processes each character exactly once, either adding it directly to the result or identifying it as part of a key within parentheses. This traversal contributes n to the time complexity. For each key found in S, the algorithm performs a dictionary lookup using the knowledge_dict.get method. Dictionary lookups are 1 on average, so the total time spent on all lookups is proportional to the number of keys in S, which is at most n. Finally, after processing the string, the algorithm joins the result list into the final string. The join operation involves concatenating all elements of the list, which requires n time. Together, these steps contribute to the overall time complexity of the solution. Now, let's combine the individual components to determine the total time complexity. Building the dictionary requires k, traversing the string s contributes n, dictionary lookups are n in total, and joining the result list is another n. Adding these together, the overall time complexity of the solution is n plus k. Turning to the space complexity, the knowledge_dict dictionary requires k space to store the k key value pairs. Additionally, the result list, which stores the final process string, requires n space in the worst case, as every character from S could be included. The algorithm also uses a few auxiliary variables like I, j, and key, which occupy constant space, 1. Therefore, the space complexity is determined primarily by the dictionary and the result list, leading to a total space complexity of n plus k. The overall space complexity can be summarized as n plus k, dominated by the storage requirements for the dictionary and the result list. To understand why this solution is efficient, let's compare it to a brute force approach. A naive solution might repeatedly scan the knowledge list for each substring within parentheses in S. This would lead to a time complexity of n*k, as every key search in the list requires k time, and there could be up to n such searches. In contrast, the current solution converts the knowledge list into a dictionary, allowing average 1 time lookups, and processes the string S in a single pass. By avoiding redundant computations and leveraging efficient data structures, the solution achieves optimal performance with a time complexity of n plus k, and a space complexity of n plus k. Let's examine the best, average, and worst-case scenarios to solidify our understanding of the algorithm's efficiency. In the best case, there are no keys in the string S, meaning there are no parentheses to process. Here, the algorithm simply traverses the string and appends characters to the result, resulting in a time complexity of n. In the average case, typical inputs contain a mix of keys and regular characters. The algorithm still processes each key in 1 time on average due to efficient dictionary lookups, leading to an overall time complexity of n plus k. In the worst case, where every character of S is part of a key and the knowledge list contains many entries, the algorithm continues to operate within n plus k time, as the dictionary ensures constant time lookups and the traversal remains linear. Mathematically, the linear traversal of S contributes n, while dictionary construction and lookups add k. Together, the time complexity of n plus k and space complexity of n plus k remain optimal, even under the most demanding inputs. When solving this problem, there are several common mistakes to watch out for. First, remember to handle edge cases properly. For example, if the string contains no brackets, or if a key in the knowledge map is missing, your solution might crash or produce incorrect results. Always validate that a key exists in the knowledge map before attempting any replacements. Another frequent issue is inefficient string replacement. Using repeated concatenations or replacements in a loop can lead to n squared time complexity, which is far from optimal. Instead, build the result using a list and join it at the end to achieve better performance. Additionally, overcomplicating the parsing logic is a trap many fall into. Writing unnecessarily complex code to identify and process brackets increases the risk of bugs. Simple approaches like using a stack or a two-pointer technique often work perfectly. Case sensitivity is another area where errors occur. The problem specifies case-sensitive key matching, so ensure your solution treats keys exactly as given. Lastly, be mindful of variations that involve nested brackets. If your solution doesn't account for nesting, it will fail in such scenarios. Always clarify constraints if you're working on a variation with an interviewer. Now, let's consider some insights that are particularly useful for interviews. Recognizing problem patterns is critical. This problem is closely tied to string parsing and dictionary lookups, which are common themes in interviews. Many string manipulation tasks can be tackled with traversal and auxiliary data structures, so focus on identifying these patterns. Efficiency is another key concern. Interviewers often test your ability to optimize naive O(n)² solutions into O(n) solutions, so make sure to highlight the rationale behind choosing specific data structures, like dictionaries for quick lookups or lists for efficient concatenation. It's also important to clarify constraints at the start. For example, does the input string include nested or overlapping brackets? Are there cases where keys might be missing from the knowledge map? How you handle edge cases, such as empty strings, missing keys, or strings without brackets, can significantly impact the robustness of your solution. Being prepared to discuss these aspects demonstrates your ability to think critically. This problem is also related to several other questions that can help you practice similar concepts. For instance, LeetCode 20 valid parentheses is a classic problem that uses a stack to match brackets, which is a foundational skill for this problem. Another related problem is LeetCode 1249, minimum remove to make valid parentheses, which emphasizes string manipulation and balancing parentheses. LeetCode 648, replace words, focuses on efficient string replacement, often implemented using a dictionary or a tree, and it shares some overlap in terms of optimizing replacements. Similarly, LeetCode 139, word break, deals with string segmentation problems that involve dictionary lookups. Studying these problems will deepen your understanding of the techniques needed for string parsing and manipulation tasks. Finally, let's explore some alternative approaches you can use to solve this problem. The two-pointer approach is a straightforward method where you iterate through the string with two pointers to locate brackets and replace substrings. While intuitive, this approach can become inefficient if not implemented carefully. A stack-based approach is another option. By storing the indices of opening brackets in a stack and replacing substrings when encountering closing brackets, you can handle nesting effectively. This is a clean and reliable method. For those comfortable with regular expressions, a regex-based approach can be used to locate and replace bracketed substrings. This method is concise but heavily dependent on regex capabilities, and it may not be the best choice for large inputs. Lastly, pre-processing the knowledge map to create a lookup table optimized for constant time access during traversal can significantly reduce runtime overhead. Each of these approaches has its strengths, so choose the one that best fits the constraints and requirements of the problem at hand. Great job on completing this walkthrough. To recap, we explored evaluate the bracket pairs of a string, reviewed different solutions, and highlighted key takeaways. Remember to practice similar problems to strengthen your skills. Thanks for watching, and don't forget to like and subscribe for more content. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!